And so, just as a reminder, if you missed this or you were too busy texting during the presentation, it will be up on YouTube in just a few minutes. Well, it'll be up on YouTube by tomorrow morning. If you go onto YouTube and Google Lawrence Chemistry Senior, you can pull up from the last 4 years all of the different ones, right? I've already gotten almost 5,000 views, but not making any money as my kids were asking. So anyhow, it's with great pleasure that I want to introduce Romare Antrobus. It's been a pleasure having him in biochem class all these years. And it was really neat, first year that we were doing active learning. Students were introducing each other across the table, and I sat in right at the moment where Romare was telling an interesting fact about himself, that he was into Korean martial arts. But really, that's really cool. And so that Romare's been accepted to Columbia grad school in biomedical engineering. Very proud, right? And he gets to New York City. And right now I've been encouraging him, since he starts in September, to road trip out to Silicon Valley, hang out with Lawrence alums, and check out the biomedical field there. But without further ado, I'll give you a quick.
So thank you, Dave, for the introduction. As he mentioned, my name is Romare Antrobus, and today I'll be presenting research I conducted over the summer at Milwaukee School of Engineering under the direction of Dr. Woo-Ji Zhang in the bioengineering department. So in particular, I researched on the path of tissue engineering, electrospinning of pectin-based nanofibers. Before I start, I would like to thank the National Science Foundation for helping fund this experiment. So to begin, I would like to start thinking about what is nano. Nano, as a prefix, means 1/billionth. On a numerical term, it means 10 to the minus 9. If we're thinking on a nanometer scale, this is what we're looking at, from about 10 to the 0, which is 1 meter, to about 10 to the minus 9 meters, which is about 1/billionth times smaller. Within this meter, there's about different amounts of groups, starting with macro scale from 10 to the 0 to about 10 to the minus 3. Micro scale from 10 to the minus 4 to 10 to the minus 6, and nano scale from about 10 to the minus 7 to 10 to the minus 9. To give you some idea of reference of what lies in each of these groupings, we'll start with macro scale. So a 1-year-old or a 2-year-old kid is about 1 meter in height, an apple about 10 to the minus 1, an ant 10 to the minus 3. Compared to micro scale, the diameter of one strand of your hair is about 10 to the minus 4. Compared to the smallest thing your eye can see, 10 to the minus 5, 10 to the minus 6, bacteria, the size, nanoscale, we're talking about today, nanofibers, 10 to the minus 7, which is about 1,000 times smaller than the strand of your hair. Even smaller, DNA is about 10 to the minus 9. So based on this scale, different types of technologies can be created. And this includes things from nanoparticles, carbon nanotubes, nanowires, and nanofibers. So nanofibers are fibers of material with a diameter of a few nanometers. As you see in this image, this is a comparison of size comparing human hair at one strand to a single pollen grain, and in the background there are nanofibers. So you can really see the 1,000 times difference between nanofibers and the human hair. So what does this nanoscale provide you? Different advantages, such as a large surface area to volume ratio. So the larger your object is, the smaller the object is, I should say, the larger the surface area it becomes. So this brings a lot of advantageous applications for these different nanofibers, including great reactivity at the cellular level. So when we're interested in creating environments between cells and nanofibers, it's very advantageous, mainly because cells are about 10 to the minus 6 in diameter. With these 10 to the minus 7 fibers, we can create great environments to do certain things. We can also tune the morphology of these fibers. We want to be able to control the functionality of what we can do for these individual nanofibers and harvest a typical environment that we want to use it for applications. So these applications include many things, starting with defense and security. So when we're thinking about chemical and biological sensors or protection. For healthcare, which we'll be talking about today, tissue engineering, tissue repair, drug delivery. In terms of energy and solar cells and fuel cells. In terms of environmental engineering and biotechnology, membranes and filters. So to give you an idea of what kind of products actually are in the market that use nanofibers, here are a few. Starting with fishing rods. Fishing rods are a great example. They use nanofibers. They are made of nanofibers, and ideally that's just due to their great elasticity and strength. To antimicrobial masks. These help for air pollution and filtration of air. To vascular access grafts that are used in dialysis patients. So these are made out of nanofibers. You place them inside of patients, dialysis patients. You take the blood out, and then with that, you purify the blood and put the blood back in. In terms of membranes, this is a membrane that can be used for air filtration, liquid filtration. You then want to be able to use them for solar cells, fuel cells. Here's another example of an in vivo type of product that's artificial bone filler that can be used inside of a patient needing that. And then for everyday use, just liquid water and trying to filtrate the liquids that we drink. So then we want to turn into how do you fabricate these different types of fibers. I want to begin by just talking how nature actually uses these fibers and how it's very important. So here's just a GIF of a spider. Spiders do not spin webs at the nanoscale, however they do spin fibers at the microscale. And they use such small scaling to take advantage of those surface areas. The small size gives a great application for surface area, so they can catch prey, hang their eggs, and such things like that. However, we do see nanofibers in nature, such as carnivorous plants. This plant in particular uses nanofibers on its surface in order to catch prey. Here's an image of us, humans, in the muscular system, where collagen fibrils that help in our muscles help for contraction and movement. So that's also on the nanometer scale. In terms of more mechanical fabrication methods, there are several, including spun bond, which uses mechanical forces, melt blown, mechanical forces, and again, electrospinning, which is what we're talking about today. It uses electrostatic forces. Comparing the three, we're looking at fiber thickness, web thickness, and production speed. In terms of fiber thickness and web thickness, electrospinning is the main focus here, and we are noting that we are able to create smaller fibers with a smaller web thickness, giving us that advantageous surface area. However, comparing production speed, electrospinning is much slower at 100 to about 500 meters per minute, and this is mainly because these first two applications, these first two methods are optimized to be used in factory settings for more products that are used in plastics and other different fabrications. So electrospinning. Electrospinning is the process of creating nanoscale to microscale fibrous scaffolds using an electric field. So basically using voltage to pull fibers out of a solution. As you see in this apparatus, you have a solution inside a syringe, and we can talk about what kind of solutions are used. The syringe has a needle, and that whole contraption is controlled by a pump. This flow pump controls the rate at which the solution comes out of the needle. A high voltage is then attached to the needle and to a collector that's a certain distance away from the flow pump. So once that high voltage is turned on, the solution jets out, creates a radial movement, and lands onto the collector, causing a creation of a fibrous scaffold. And this, I should note that this technology has been around for hundreds of years. However, startups, researchers, labs, and universities haven't started using it until the early 2000s due to this great application. So, fiber formation. How does this fiber actually get formed? So as you see, I have my electrospinning tip and a target where the fibers will be collected. Without an electric field, you have your droplet on the surface of the tip, being holded by surface tension and gravity pointing down. When an electric field is created, it deforms the droplet on the tip, creating a Taylor cone, and the solution jets out with slow acceleration. After a certain point, radial movement starts, and this is your zone of transition between liquid and solid. This is your rapid acceleration. This is where the fibers are collected, and you can analyze from there. So what causes the Zona solidification? This is due to the distribution of charges within this fiber or the solution throughout the time it's in the air. When you charge your liquid, over time the charges move to the surface of the solution, therefore causing it the solidification. The charges end up on the outside and you can collect your nanofibers. So here's a GIF of the actual electrospinning process. I'll rewind it. You'll actually see the Taylor cone form and then the radial movement. So what kind of materials can you use for this process? You can use metal oxides, carbon, and even polymers for this electrospinning method. In particular, today we'll be talking about polymers just because we are ideally using this for applications in healthcare. However, this great diversity of materials allows us to use various amounts, metal oxides for fibers that you want to use for great conductivity or other applications that you're interested in. In particular, polymers, that's what we're talking about today. Polymers means, poly means many, mers parts. In chemistry, polymer chemistry, we're talking about macromolecules with a molecular structure consisting of small or large amounts of smaller, similar molecules unit bonded together. So here we have one unit of a molecule. This N represents the amount of times it can be repeated. So ideally, this is your larger macromolecule, and this is what's going to be used as your solution in the electrospinning process. So there can be different types of polymers that you find. Synthetic polymers are the ones that are man-made. These are your plastics. This includes your nylons, polyethylenes, polyesters, polyestrines, things that make your clothes, plastics in the world. Your natural polymers are what you find naturally in the environment. These include silk, DNA, starch, and pectin. Pectin is highlighted mainly because we are focused on that today as a natural resource. Pectin. Pectin is a natural biopolymer found in nature. It's found in the primary cell walls of plant cells, so carrots, apricots, apples, oranges. As a natural biopolymer with a heterosaccharide linear structure. So as you see, this is your polymer. You have repeated chains of the sugar. And you want to be able to use this for several reasons compared to your plastics. These are more biodegradable, biocompatible, cheaper than your plastics, so you want to be able to use a more natural resource for different applications in healthcare. So the overall goal, we want to be able to create a nanofibrous scaffold on your collector that mimics the extracellular matrix seen here. The ECM, or extracellular matrix, is the part of a cell that provides the structure, the strength, it holds the cell together and helps different cells next to each other communicate with one another. It can achieve those things due to its function, due to its structure. So structure helps its function. Ideally, we want to be able to mimic that. If we can create and harvest nanofibers with a certain structure similar to extracellular matrix, we want to be able to similarly mimic the function of the ECM. And this includes increasing structural support for cells if we place cells into these nanofibers, increase cell proliferation, increase cell communication, and control the functionality of these cells and fibers so that we can potentially use them for different applications. So the problem statement. Many synthetic polymers with cytotoxic solvents have been electrospun to fabricate nanofibrous scaffolds for in vivo biomedical applications. So if you remember with the vascular grafts, imagine those are made out of synthetic polymers with cytotoxic solvents. Those are grafts being placed into the human body. Those can be very detrimental for patients, and we want to be able to use more natural resources so we can eliminate that problem. So my goal today, or throughout my research, was to be able to fabricate biocompatible pectin-based nanofiber scaffolds without cytotoxic solvents by applying optimal parameters in an electrospinning process. So previous research looked at the electrospinning of alginate. So alginate, similar to pectin, is found in the cell walls of brown algae. It is a natural biopolymer with a linear polysaccharide structure, seen here. So you have your, again, repeated units of this alginate structure. This research in particular looked at mainly what type of alginate solution is needed in order to create nanofibers that have a similar matrix to the extracellular matrix. Similar structure to the extracellular matrix. So this included alginate and a carrier polymer, which we'll talk a little later. This mixture created a nanofiber scaffold that looks similar to this. Now you still have your nanofibers that are uniform. However, you do also have these beaded structures. These beaded structures are just an accumulation due to accumulation of alginate due to your concentration of alginate that you used and also different electrospinning parameters. This research then looked further, how can we eliminate these beads? This included using surfactant. Surfactant I'll explain a little later, but just know that the addition of surfactant helped reduce bead size and create a nanofibrous structure that will mimic the extracellular matrix. So my methodology throughout this research included creating several Pectin solutions, electrospinning. Here's my actual setup where I have a flow pump with my syringe and polymer solution, a voltage generator connected, and a collector. The collector is nothing fancy, it's just a book stand with foil on top connected to the voltage generator. We then want to optimize the fibers that we created via these different solutions, via changing the Pectin solutions, and then also optimize the electrospinning parameters to further create better nanofibers. We then want to further optimize this process by cross-linking. Cross-linking is a further optimizable method, and I did that via cross-linking with calcium and oligochitosan, and this prepares the fibers for further applications for healthcare. So these Pectin solutions that I used, this included producing 5 Pectin polyethylene oxide PEO solutions. Polyethylene oxide is my carrier polymer. I created different ratios, including 70-30, 60-40, 50-50, 40-60, and 30-70. Each of these solutions included a 4% by weight Pectin, 4% by weight polyethylene oxide, and 2% by weight surfactant chloronic F127. We're going to go through each of those ingredients. Polyethylene oxide, PEO, is a carrier polymer to aid electrospinning. So as you see, this is the polyethylene oxide molecule. This end is representing the amount of times it's repeated. And it can improve electrospinning by improving chain flexibility between polyethylene oxide and Pectin. It reduces the charge repulsions between each Pectin molecule, and also increases hydrogen bonding. So depending on the ratio that I use, you get different results in electrospinning and different types of fibers. Chloronic F127, the second ingredient that's added, is my surfactant, and that is also to aid electrospinning. Here's the molecule, it's another polymer, and it can aid electrospinning by reducing surface tension between the Pectin and polyethylene oxide. We then want to do some characterization of these different solutions. So in this graph, we have Pectin to PEO ratios on the x-axis from 70-30 to 30-70. And then on the y-axis, we looked at the viscosity of each of these solutions. As you can see, the more polyethylene oxide that's added, the more viscous this solution. The concentration of these different solutions affect, as I mentioned, the different types of fibers and different types of electrospinability matrices I can create. The electrospinning parameters that I used included fluid parameters, environmental parameters, and process parameters. In terms of fluid parameters, I was able to control concentration of viscosity by using different amounts of Pectin and polyethylene oxide, surface tension by the surfactant. Environmental parameters were controlled mainly by ventilation and controlled temperature. I decided to work in a controlled environment, which would be my lab hood. In terms of process parameters, I wanted to control voltage and current. Also the spinning distance, the distance between the tip and the collector. And also solution flow rate, how fast the solution is coming out of the tip of the needle. So here's a table of the different initial electrospinning parameters that I focused on. On the left are the parameters, on the right are the levels of each parameter. Pectin to PEO ratios, as I mentioned, were the 70-30 to 30-70 ratios. The distance between the nozzle and the collector was about 15 centimeters. The nozzle size, 24 gauge. Flow rate was about 1.19 milliliter per hour. Voltage, 11 kilovolts. And current was about 0.375 milliamps. We then wanted to electrospin all of these solutions and then see what type of fibers we created. And we analyzed that via atomic force microscopy. This AFM is a microscopic technique in order to produce high-resolution images of items on a nanometer scale. So as you see the schematic, I'll briefly just run you through it. Here's your sample. These were where the nanofibers would be. You have a tip that scans that surface, a laser that excites that surface and creates an image through the sensor. And we can analyze these fibers for several reasons: to confirm the fabrication of uniform fibers that would mimic the extracellular matrix, and analyze the morphology of these fibers. Are we getting beads? Are we getting different types of formations of fibers? What can we do with them? So here are the first results of these different ratios. Here are the high-resolution images. So figure A is showing the 70-30 Pectin to PEO ratio. Figure B, 60-40. Figure C, 50-50. And figure D, 40-60. As you see, there is no 30-70 ratio because due to the high viscosity of that, due to the polyethylene oxide, we were unable to electrospin it under these different parameters. So starting with figure A, it's kind of hard to see. However, the fibers are lightly shown and bead formation is there. Compared to figure B, you see better fibers that are formed, less bead structure, and smaller beads. Figure C, a lot more bead formation. However, we still do have the uniformity of these fibers. And figure D, same thing. We have larger beads, however, we still have those fibers and a uniform construction. To analyze these further, the AFM was allowed to give us different diameters, the average diameters of each of these fibers. The x-axis here is showing, again, the different ratios of Pectin to PEO. The y-axis here is showing the diameter in nanometers. So the average diameter for figure A, the 70-30, was about 3 nanometers, which is probably why you can't really see them. For figure B, ratio 60-40, you have average of nanofibers about 27 nanometers. Figure C, 50-50 ratio, you have about a ratio of diameter of about 4 nanometers. And figure D, you have the ratio of 40-60 with nanometers at the size of about 6 nanometers. Based on these, we are trying to pick the best one. However, we want to see which of these solutions gave us the ideal structure of the extracellular matrix, and we just went with the 60-40 solution, mainly because bead size was smaller compared to all the other solutions, and also we got more uniformity in these fibers. We then went to optimize. Optimization was key in order to eliminate these bead size and mainly try to get those extracellular matrix structure and function. We did that by changing and adjusting the fluid parameters. This included modifying the solution slightly to 65 to 35 Pectin to PEO ratio. So we dimmed down the polyethylene oxide to make it less viscous and tuned up the Pectin ratio. We then went to vary the pluronic F127 concentration to about 2% by weight, 5% by weight, and 10% by weight. As you remember, pluronic F127 is controlling that surface tension between the two solutions. AFM then allowed us to analyze these different fibers again. Figure A is showing this 2% by weight pluronic F127. Figure B, 5% by weight pluronic F127, and figure C, 10% by weight. As expected, figure A is what we used in the last, these are the ingredients that we used in the last initial testing with the 2% by weight, so we expect these bead formations to still be there. With 5% by weight pluronic F127, we were able to eliminate the beads, create a uniform fiber shown here. Figure C, similarly, no bead formation, and we still have that fiber formation that's uniform. However, if you look closely around the fiber, there is a bit of a distortion, and that we lead to a called leakage. I believe it's leakage mainly because pluronics concentration might be so high that surface tension is so low, the fiber structure could not hold itself together and cause leakage of the fiber itself. We then believe that the optimized solution is a 65 to 35 Pectin to PEO solution with a 5% by weight pluronic F127, mainly because it, again, produced uniform fibers and a nanofibrous structure similar to the extracellular matrix. As you see in this image, here's another glimpse of a fiber created by the solution. So then we want to further optimize this solution in fibers and prepare for possible applications via cross-linking. Cross-linking is a process to preserve nanofiber structures in aqueous environments. So if you remember the fibers I just showed you, if you place those in water or aqueous environments, they would just dissolve. We want to be able to treat these fibers in a way that we can solidify them and have them ready for applications in healthcare. Cross-linking fibers look similar to this. Add that treatment and the fibers will look more like this. These are from the Alginate study. So the cross-linking goal, we want to be able to produce functionalized nanoenvironments. If we wanted to integrate these cells into these nanoenvironments, we want to have good interactions between the two. We want to be able to see self-renewal of cells, proliferation of cells, migration of cells, and enhancement of phenotype. All the things that the extracellular matrix can already provide those cells. In this image, this is a study done at Johns Hopkins where they integrated stem cells into nanofibrous environments and were able to really see the self-renewal, proliferation, migration, and enhancement of phenotype of these different stem cells. So this procedure consisted of electrospinning, of course, doing an ethanol wash, cross-linking with either calcium or oligochitosan. Oligochitosan is another natural biopolymer, which is why we went to it as a cross-linker, mainly because we're trying to go for all natural purpose. It's similar to chitosan, which is found in the shells of lobsters and sea animals. And that created our nanofibers for applications. We then used the scanning electron microscope, which is another microscopy technique, in order to image these different cross-linked fibers. Figure A is showing not cross-linked. Figure B, cross-linked with calcium. Figure C, cross-linked with oligochitosan. Figure A, unfortunately, is showing those beaded formations again, due to possibly we need to do further optimization. However, we still see the the uniform fibers. Figure B is not showing any fibers at all. You'd rather see residues of calcium on the surface, leading us to believe that calcium is not a good cross-linker for this. Calcium was a great cross-linker for alginate solutions, but maybe because of the structure difference between alginate and pectin, calcium was not able to be used as a cross-linker. However, oligochitosan, which was greatly appreciated, was used as a cross-linker and showed the remains of fibers to be in touch. So we still were able to cross-link and provide fibers that were cross-linked, and as you see, beading formations were still there. Conclusions, I decided that our optimal solution was a 65 to 35 pectin to PEO solution with a 5% by weight chloronic F127 cross-linked with oligochitosan. These are more images of these fibers. Bead formation is noted right here. The good thing is these beads are not as rounded as we would expect, so we're on the right track to minimizing bead formation. And future directions. We want to further optimize, as I mentioned, with chloronic F127 to get a fully uniform fiber. And then functionality testing. What can we do with these fibers? Can we test them for tensile, how strong they are? Can we test their conductivity? What can we use them for in terms of electricity? And cell studies. Can we integrate cells into them and to see if they replicate faster, proliferate, communicate faster? I would like to thank the National Science Foundation and Milwaukee School of Engineering for helping me fund this experiment. I would also like to thank Dr. Guji Zhang, my advisor at Milwaukee School of Engineering. I would like to thank Dr. David Hall for guiding me throughout this presentation, the Lawrence University Chem 680 class, and also the MSOE staff that helped me through this. Questions?
So you were saying that when you have originally done the electrospinning to make the fibers, that they're not great in the aqueous environments, but then you're cross-linking them with like ionized calcium. So is that an aqueous solution of the calcium?
Yes.
And then
So we just soak the fibers into a calcium solution.
Okay, so they don't like break down on the time scale that it would take for them to cross. Okay.
Several.
Yes.
Really cool stuff. So I I'm curious about the molecular weight of the PEO that you used. Was this a long chain, or like, do you know how PEO was it?
I would have to look at my paper. I
Cool.
don't remember.
Because there's a lot of work that's been done on the viscosity of the much longer polymers. You're going to have much higher viscosity, but there's also PPO. Have you ever thought about using polypropylene oxide?
I haven't.
Okay.
We use PEO because of the alginate paper.
Okay.
It was a great copolymer to use with alginate, so we just went with that.
Yeah, PPO or PEO is notorious for having really high viscosity, and
Yeah.
it's like solid at room temperature. It's really annoying.
I mean, use one of those the glass viscometers.
Yeah,
so we had to wait
viscometer.
like hours for it to.
Bless your heart. Honestly, my other question was, what temperature were you keeping your solution at before the electrospinning happened? Was there any sort of
Room.
temperature control?
Room
Just
temperature.
room temperature?
Mhm.
Cool.
What was the solvent for the?
Water.
It was water.
So we tried to make it as minimal toxic as possible.
Yeah. And then one last question that, sorry, this is so cool. I'm taking frantic notes. And so the fiber that you make in the end, is it that the pectin is all that remains and the PEO is just a carrier to help the pectin be what comes
Yeah.
through? So it's just a pure pectin thing that comes
Yeah.
out at the end.
And I believe the ethanol helps remove more polyethylene oxide
Cool.
further.
So in terms of any sort of surface structure, have y'all gotten any images of like what the type of, I guess the structure of the fibers themselves, like are they, their densities or any sort of like structural aspects of them?
For now, all we have is really the diameter.
Cool.
We weren't able to, like those final images were taken the last day I was in the lab, and the person who's taking over in the summer is going to be able to test that further.
Okay, because I don't even know how you would actually take those images or like know that information, but it'd be really cool to see.
Other questions?
Gus?
Yeah.
Oh, let's see.
Oh yeah. So for the AFM data, do you have standard deviations for those as well? No.
No.
That was
I laughed because I'm trying to submit the paper, and they asked the same thing. So
yeah. I mean, it would have been really nice to see that, like, see if the diameters are consistent across them.
Yeah. So there was no correlation between ratio and.
But I guess. Sorry. Go ahead.
Yeah. Go ahead.
I guess from the images too, you can see like you're gonna get a pretty good idea for how the size is, how consistent the diameter is.
Yes.
So you see like the fiber thing, that the result of cross-link thing. So this is just a simple question because I'm not a science major, so I'm not gonna pretend like I know what I'm saying. So
That's questions.
so what is kind of like the real life application of those fibers? So are you trying to find ways to like effectively produce the fiber and like then have like real life applications to it, just like the one that you said?
Yeah. So this research was mainly looking at the fabrication method. Later research can be used to see what you want.